we have here a system of two linear equations in three unknowns x1, x2, and x3. We easily solve this system by adding multiples of rows to rows, non-zero multiples of rows, and multiplying rows by constants and so forth, by the usual row operations. And the operations are simple enough. We multiply the first equation by 1/2, and then we add -4 times that equation to the second equation. Then we add, it turns out, 3/16 of the second equation to the first, and we get this. And then we can't do any more. We can't eliminate any more variables, leaving x3, let's say, well, it leaves us with one free variable. So we're going to just choose x3 as the free variable. That's the most convenient. And we set that free variable equal to our parameter t. Doing so, if we solve for x2, well, we're going to add 3/8 of x3 to both sides, and that's going to be 3/8 t, so we're going to get x2 is 19/8 plus 3/8 t. x1, similarly, is going to be 15/16 plus 1/16 of t, minus 1/16 of t, because now x3 is t. Okay, so that by choosing any value we wish for t, we get values for x1 and x2. So x3 is free. x1 and x2 are determined by the value of that free variable. And we incidentally say that the rank of the system is 2, because you have one free variable and you have three variables. That leaves the other two as not free, as determined by the value of the free variable. Okay. We also comment that we can take this solution now and write it as a column vector, where x1 equals, well, what you see here, 15/16 minus 1/16 t, x2, what you see, and x3 is t. Now we do something with this, because it's kind of an important rearrangement. We have t terms in each of the three rows, and we have constant terms in each of the three rows. Now the constant term in the third row is 0, but that's okay. So what we can do is we can say, okay, well, I take these t terms. We have -1/16, 3/8, and 1 multiplied by t. So I could express these three terms as a column vector, -1/16, 3/8, 1, and factor the t out. So if I multiply t by this, well, you see what I get. We understand this. And then I take whatever's left over after I've taken the t terms and put them into this column vector. And that means that I take the 15/16 and the 19/8 and I put them into a column vector. Of course, I need something for the third number in the column vector, but that's going to be 0 because we're not adding anything to t. And now I've separated this out. Now there's a profound interpretation in terms of linear transformations and vectors in space that we'll talk about. But right now we just see this important rearrangement. Okay, now it's a little less cumbersome to do the row reduction without having to write out x1, x2, and x3 every time. And we do that, and this is something we should be familiar with now, but we do that by writing an augmented matrix where the numbers in the first column represent the multiples of x1, second column multiples of x2, and so forth, and the numbers to the right of this dotted line represent the constant numbers on the other side of the equal sign. And we do the same operations that we did over here with the rows of this matrix. See? So we take half of the first row, and then we add half of the first, okay, we add -4 times that first row to the second, and so forth. The same operations we did here, although we could do a different set of operations, and we end up with this matrix. This matrix has the same meaning as this system. Again, we understand that. This matrix has the same meaning as this. This matrix has the same meaning as this system, which means that this matrix gives us a solution that's identical to the solution we got here, and right there's the solution. Okay. Now we can also write this as a matrix equation. AX equals B, where A is a matrix. You see the matrix here. X is the column vector, x1, x2, x3. And B is your vector 9, -1, the target vector. So we're trying to find the value of the x vector that gives us the target vector, and we do that by matrix multiplication. Although, in this case, the way we solve this matrix equation is we convert this equation to the augmented matrix and solve the augmented matrix. Now, when this is a square matrix, we can do a matrix inverse. If it's a square matrix, non-singular square matrix, we can do the matrix inverse and shortcut the whole process. And we comment a little bit on the idea of rank again. Okay, so we've got 2 rows in this matrix. We don't end up with a row of zeros down here, so the rank is 2. Okay, in other words, we have full rank. The rank can't be bigger than the number of rows. Turns out to be what we say is the number of independent rows, linearly independent rows. And if we don't get a row of zeros, then all the rows are independent, and we say then that we have full rank. Full rank equals the number of rows in the matrix. And we also say the matrix A can be reduced by itself. Well, it's been reduced up here. We just write it down without the right-hand side. We reduce it, and we see that it has 2 rows. We don't have a row of zeros, so again, we have full rank, or rank 2. This idea of rank is going to be important, but the main idea here is that we can write this system as an augmented matrix or as a matrix equation. So we have 3 equivalent ways to write things, and then we can determine things about the system.